So yeah, and in DFT, the main function is the density, so we call it N, and like it's a three-dimensional space. So in your crystal or in molecule or anywhere, your electrons take a certain distribution, and you look at it, this distribution, you call it electron density. It's a probability where the electron would be.
The electron cloud.
And now, depending on this, all the property of materials can be calculated based on this density. So that's why we call it density functional. So density defines everything. So in a real system, so let's say you have an atom, you have electron. So in a fairly complex system, and we will be working with thousands of atoms, so it means we can have 10,000 electrons. It's a lot of. And imagine you have a very basic system, not like
just one,
like a moon and the sun, or and Earth. So a two-body system we can solve analytically in gravitational, right? But when you have a three-body system, it's impossible to solve analytically anymore. So this is like many-body system, and in electronic structure properties, it's the same problem. You can solve easily a solution of, so this is hydrogen plus proton, basically, proton. So it creates this 1/z field, and you put an electron here, and where electron would be in this potential. So this is our distance, and this is our energy potential. So where would the electron sit? It will be sitting somewhere here, in this well. It's a two-body system, we can solve it analytically. As soon as you start making a three-body system, you cannot solve it. When you have a 10,000 electron system, it's impossible to solve it. We just don't have such computers. And this problem scales exponentially because each pair of this interacts and changes with time every time.
When we make it, doesn't it form like a lattice? So then they're all.
It
all
forms
like
a stable
out.
configuration, but you still need to know all this interaction. So there are certain ways to deal with this. So first of all, in each atom, let's say we have a heavy atom, I don't know, gold. So it has many levels, many electrons. So it has 1s, 2s, 1p, 2p, 3d, 4d, 5d, 5s, lots of electrons. So most of them are sitting in the core, so they are so tight that external electron almost doesn't care about them. So we kind of throw this away and look only at the valence electrons. And the valence electrons is probably 5s for gold. And these guys are represented with some screened potential. So these are protons, many protons, creating this field, but around them floating are many. So this is our core. So I don't know how many, it's like 50 plus, right?
There's probably like just one thing for the shielding.
And you have also 50 electrons floating around it,
but they don't interact. They barely interact with the valence.
And the valence would be much more spread because valence. So these guys which are very close, they will screen all this plus. So all of them are minuses, and these guys are pluses, and they will cancel out. And because of this, the valence electron, which is much more spread, is pretty much well described. This can be cancelled out.
Okay.
And this approach is called pseudo-potential. Pseudo-potential means that instead of real potential, we take a screened potential and cancel out. This means that instead of 50 electrons, we calculate only 2 or 1.
Just the outside one.
The outside one. So this reduces the amount of calculations. But still, you can have, in a row, you can have 18 electrons. So there are still elements with up to 18 electrons in the valence shell. Especially transition metals. All of these d orbitals, d10, right? So let's say we have 3d8, 3d9 transition metals. These guys should be included in the valence shell because they are most important because they create all these magnetic configurations which are important for transition metals. So we would routinely have like 10 electrons per atom still in the system. So that's why if we had 1,000, we would have 10,000 here. But so there is a famous theorem, Kohn-Sham theorem. They got the Nobel Prize for this, for saying that we don't need to calculate interactions of these 10,000 electrons between each other, but we can take one electron in this in a field of all other electrons and solve a single particle problem. So that instead of solving 2 particle, 3 particle, 10,000 particle problem, which is impossible to solve, we solve only 1 particle problem in a potential. And this potential, so now this potential is, there are few things. So here we had this atomic potential.
Now they're basically solving the atom's interaction between that one electron.
Yes.
Okay.
So we have atomic potential, so our ions. So this is ion 1, ion 2. So it gives us potential, let's call it V of R. It's basically 1 over R, Z over R, plus all the atoms in the system you have. So R minus Ri, let's say. This is real electron, this electron, and this is ion. So distance, so if my electron is here, so it will feel this guy and it will feel this guy, it will feel all other guys with a very simple potential. There is one term which is kinetic, and there is a term which is called another, let's say call it V, V Coulomb. We call it Coulomb. So this is electron.
Yeah.
So forget about these guys. Now we don't take electron one by one, but we take electron with the rest of electronic field. So this guy depends on density of electrons. This guy does not. This guy depends only on it's a sum. It's just very discrete. This depends on density. That's why we call all this thing of density functional, because it depends on the function, on the density. Plus there is one more term which is called exchange correlation. It's a term, it's again electron, and it describes all these many body interactions. So which comes not just from Coulombic interaction, but it describes Pauli exclusion principle. So basically if you take this electron and swap them places, energy will change. And this term is the most complicated term. It also depends on this density. And like this is the basis of making a better density functional theory. So nobody knows the exact form of this thing. There are some approximation, and because of this, any kind of calculations you do will never be accurate, because the exact form of this term is not known. So all of these guys, so we sum them up, and this is technically this is energy, right? So in classical mechanics this would be energy. In quantum mechanics it represents the energy operator. We call it H, and operator sets like this. So it's an energy operator, we call it Hamiltonian, because the guy who invented it was Hamilton. And so these guys are technical also operators, but they are very, very simple because they're just numbers. These guys are not numbers. So what happens is that when we try to solve, so what we solve actually in quantum mechanics is H psi equals E psi. So this operator, and we are trying to find its energy, and psi is a wave function. So psi is technically n, and psi is the same thing. N equals psi square.
But right now, because we have two basically unknowns.
So what happens is that when you try to solve this, you're finding both this and this. So this is called eigenvector. It's from German. Eigen means your own or proper or something like that. And eigenvalue or eigenvectors, because usually you have many. So if you have 10,000 electrons, you will have a vector of 10,000 here.
I learned this in calculus.
All possible values, all discrete values that electron can take. So when you try to solve this, you will get as a result this psi, or which is the same as n of r.
So range of answers,
R,
basically.
right? Of r. Solution of this equation gives you the density, but you see that the equation itself contains density. So that's why it's kind of interrelated, and doing it once you cannot get the right answer. So what you do,
You have to loop it.
you take some initial guess. You say, let's assume that this, to calculate these terms in this equation, I will guess some initial n. And let's say I would say I will take a non-interacting system as if I just put my non-interacting atoms there and assume this is my initial density. You will solve this equation and you will get n1, the first iteration. And you will say, okay, if this is slightly better, so this and this is not equal, so this n0. It's not equal. So you take this again,
Put it back in.
put it back, solve again, you get n2. Solve it again, you get n3, and eventually it converges. So it becomes more and more stable and accurate. So you do it many times until you reach some degree of convergence, so that you see that your delta n is not changing anymore. And that's why this process is called self-consistent cycle.
And that's why they need the CPU to do it.
The reason why you need CPU is because this equation is written in a, so as we said,
the matrix
we have 10,000 eigenvalues.
Yeah.
The eigenvalues and eigenvectors. This psi is at 10,000 by 10,000. 10 to 4, 10 to 4. And this h is also at 10 to 4 times 10 to 4 matrix. And actually it can be even larger because to represent this electron density, we do not just take this single level, but we create more orbitals for each of them so that you describe it more properly, so that you have all possible shapes of different orbitals as a basis on which you can expand any function. So it's like Fourier transform. Fourier transform, you convert your function into a sum of sines. Here you get your n function. You expand it into a sum of some basis functions. And these basis functions can be plane waves, so that would be explicitly Fourier transform. So this method is called plane waves basis. Or this phi can be a sum of real atomic orbitals. And still you want maybe to try to modify these orbitals a little bit, compress them, extend them, so that they create a more complete basis, so that it's a sufficient basis to describe your function. So basically when you have this matrix, that's all you have. It's non-zero everywhere. And to solve this equation means to diagonalize. Diagonalize this matrix so you get only values here. And these values are exactly the eigenvalues that you care about. This is standard procedure anywhere, like any kind of physics calculations will boil down to a matrix. DFT, any kind of partial differential equations for heat transfer, for light propagation, and so on. Everything boils down to a matrix. And then solving this matrix. And the problem is that this procedure scales up as n squared. So if this is size of the matrix, it goes as n squared or sometimes even as n cubed. So that's why it's very expensive. You can easily calculate 10 atoms, but when you go to 100 atoms, it's not 10 times harder, it's 100 times harder. So this is what DFT is about. And there are a bunch of different approximations for these guys. So some of them are called LDA. This is the simplest one. So this is called local density approximation. It takes the form of this guy to be equal to explicit analytically known expression for free electron gas. So when the n is almost flat everywhere, then you can solve it analytically. So local density. The next approximation is called GGA. It's a generalized gradient approximation. So when the n is not flat, but it has some abrupt changes, you need to take into account not just the value of n in this point, but also a gradient of n in this point. And then it will give you a more correct answer. And there are like a bunch of even more complicated methods here, which are even more. So we'll be mostly working in this regime. It's more relatively fast, so this is really doable. And there is a bunch of ways, of numerical methods to speed up this diagonalization. Try to make this matrix sparse, try to use different solvers, try to use some preconditioners to solve this matrix, like invert this matrix and solve this. So those are numerical methods which we really don't care about. But in different programs, they are implemented all in different ways. So all the machinery is there, DFT is the same, but every program implements it in a different way. That's why some of the programs which said, okay, we will only work with semiconductor systems. And that's why we can make even further approximations.
They can fine-tune it better.
And fine-tune it better. It would be super fast for the semiconductors, but it's not going to work for metals. Or for metals, it will just use some conventional methods which are not fine-tuned, and then it's just going to be slow.
So technically we need to find approximations for the transitional metals to add into the formula to fine-tune it.
It's all in there. It just, for us, we should know which program is suited for which type of problem and just use the appropriate program. So it's also like, there are small things like to know. So LDA overestimates the interaction between the atoms. This guy underestimates the interaction between the atoms. So if you calculate some crystalline structure, LDA lattice constant would be smaller than experimental. GGA lattice constant will be larger than experimental. So you need to know these tiny things and just to know, okay, I've calculated this value, compared it to experiment, it's 2% larger. Is it okay, or am I doing something wrong? That's okay. But if you got a lattice constant which is 2% smaller than experimental, then you are doing something wrong, because GGA should be higher. And in a similar way, like there are van der Waals interactions, especially like in organic systems. Carbon, anything organic. So non-covalent, covalent interactions, just two molecules completely independent, like two benzene rings. There is an interaction between them, which is really poorly described by DFT, because this van der Waals interaction is a dynamic process of this molecule getting slightly more polarized temporarily. So these electrons, so you have, let's say you have your,
they're wobbling back and forth.
Yeah. So you have your benzene ring,
Mm-hmm.
and your electron from DFT, if you solve it, it will be like a perfect donut.
Mm-hmm.
But in reality, this donut
But there's like a time
is
aspect.
fluctuating there,
Mm.
and because of this fluctuation, it kind of creates a dipole at every
Temporarily,
time,
yeah.
temporarily, and this dipole will interact with the next dipole, and it's a super weak interaction, but it's super important in organic systems, for example. In our case, maybe not so much. So you should know that if you calculate these two benzene rings with LDA,
Mm-hmm.
you will get some interaction van der Waals. If you calculate with GJ, you won't see any van der Waals interaction.
Mm-hmm.
So again, depending on your system, you need to adjust which one do you want to use. Sometimes people go to some young students go to a conference and present, oh, we spent this whole year calculating this van der Waals interactions
Mm-hmm.
between the molecules
Mm-hmm.
in DFT,
Mm-hmm.
and people start laughing at them because DFT does not describe the van der Waals interaction. So you'll catch all these small things like in the process while you are calculating this, and like new terms will show up.
How are we gonna use this, like functionally wise? How will we be utilizing this for our project?
So we would want to know. So usually, what DFT gives you is this. So there are three things you get from DFT. From a DFT calculation, so you will get energy,
Mm-hmm.
total, so it's called total energy. So it's a sum of all. Basically,
Yeah.
this.
Uh-huh.
It's a sum of ionic contribution, sum of electronic contribution, and so on. It tells you the full energy of a system.
Mm-hmm.
Then it gives you this density,
Mm-hmm.
and it gives you this value called density of states. Basically, these levels,
Okay.
or all of these levels, these are technically your energy levels
Mhm.
in your system. Because you have 10,000 of them, you will have 10,000 of them. That's why, because there are so many, we call them density. Because instead of drawing all these levels like this,
Mm-hmm.
it can be a bit sparse, a bit more dense here, a bit less dense here. So instead of drawing them like this, we will like integrate and smear them out, and we'll plot some density. And here you have a peak, and here you have
Okay. Yeah.
So this is called the density of states. So
Mhm.
this is energy, and at every energy, how many states per unit energy we
Mhm.
have. These are pretty much everything we get from there. What is this useful for? So in this density of states, you can say, my oxygen atoms, for example, are all giving me a rise of states here.
Mhm.
My metal atoms give rise to states from here.
Mm-hmm.
My Fermi level, so how many electrons I have, is somewhere here. So these states are filled, these states are empty. And based on this, you can do some analysis. What do you, like, if you want to dope your system, you can move this Fermi level somewhere here. Depending on, especially these are transition metals, so they're kind of semi-filled. The Fermi level is exactly in the middle of this band of states. And because of them, half of them are empty, half of them are filled, and all kind of magnetic effects start to appear. Because there are a bunch of states which are close together, and you can polarize all electrons like this, with a spin like this, or all down, or you can make up, down, magnetic, non-magnetic configurations.
So we need tighter densities, basically.
You would need to, well, magnetic systems are problematic because this configuration and this configuration and this configuration are very, very close in energy. So when you solve for DFT, it will try to find the lowest energy minimum, but it's kind of hard because it's like multi-dimensional space.
It doesn't
again.
separate, yeah.
So it's not necessarily that it will find it. So you might need to initialize this configuration separately, fix it, and calculate its energy, and only then compare the energy. So this are all the problems coming from magnetic systems, which let's not bother about them right now.
Okay.
density sometimes is useful, especially, so again, you have your states, and you can look at every state here. So as we said, let's say we have this state here, and you can draw a wave function which corresponds to this state.
Mm-hmm.
And most likely it will just sit over the entire crystal. But if you have some defect inside the crystal, you will look at the density or wave function of this guy, and you will see that it sits exactly on this defect. So they are very complementary,
Mm-hmm.
just to visualize where electron is.
Mm-hmm.
And it's like whichever is easier, to look at this or to look at this.
Okay.
If it's very localized, it's a signature that it's going to be a defect.
Mm-hmm.
And the total energy, so yeah, we got the number. So
Mm-hmm.
what do you do with this?
Just
It's
capacity.
useless.
Oh, it's not.
Well, just by itself.
Mm-hmm.
But if you compare it to something, then you can do some comparison. So for example, I have a system with my defect sitting here, or I have my system like a crystal
Mm-hmm.
with a defect sitting here, or
And then we can compare
like
energy.
creating a paired defect or creating a separate defect.
Mm-hmm.
So now you have total energy 1 and total energy 2,
Mm-hmm.
and you can say, okay, this is larger than this, and the system will always try to get, not just try, everything aims to get to lowest energy possible. So if there is such a configuration with lower energy, it will find it. So it basically means that experimentally you will find only this configuration.
Mm-hmm.
This configuration will never exist because it's higher in energy.
Mm-hmm.
So that's how you use this total energies to tell which configuration is more stable. Or if you have some surface and some molecule attached to it, and you can say how much energy it will take to detach this molecule and fly away.
So right now we're using DFT just to find the configuration of how we're going to make the battery. And for quality control.
For batteries, we're gonna have this call with the guys tomorrow.
Okay.
They have explicit questions, what we don't know, what would be nice to get from DFT calculations. Right now, I don't know. What people mostly focus on lithium-ion batteries is that, let's say you have a crystal. You want it to be, well, first of all, as we said, there is a bunch of different crystalline structures. These transition metals, especially when you start mixing ternary, quaternary alloys, you want to have a single phase material. But let's say I mix lithium nickel plus manganese.
Mm-hmm.
Nickel oxide, manganese oxide. So nickel oxide likes one crystal structure, manganese oxide likes a completely different crystal structure. When you start mixing them, what kind of structure will you get? Will you get yet a third crystal structure, or will you get a phase separated, a mixture of two crystal structures? So these are exactly total energy calculations. You will just try to mix in various possible configurations and see, does it like to be stable? Does it like to phase separate? Does it like to go from this type of crystal structure to another crystal structure? And why is this important? Because there are crystal structures which are called layered. So let's say something like this.
Mm-hmm.
And in this structure, lithium comes here and it can diffuse easily.
Mm-hmm.
So that's why layered structures are good, because they are conducting lithium very easily. Alternatively, maybe somewhere very close in energy, you get a crystal structure which is a perfect cubic structure. And then lithium just sits here and maybe it can hop, but maybe this barrier of hopping is too high.
Mm-hmm.
So all of these types of calculations can be done. There is actually a lot of stuff already done for single, maybe even for binary materials. So there is a website called Materials Project, and it actually has been started explicitly for lithium-ion batteries. You have to register, but it's still free for use.
Materials.
Project.org.
Okay. And all the percentages is where the machine learning comes in.
We'll get there.
Okay.
So these guys have calculated a bunch of different single composition materials, maybe binary materials as well.
Mm-hmm.
The problem is when you go to ternaries or when you go to materials which are, let's say, 10% nickel and 90% manganese.
Mm-hmm.
So it basically means 1 in 10 atoms. So you need at least 10 unit cells to describe these materials. And because of 3D structures, maybe you need 30 unit cells. So now, instead of calculating the system for 1 unit cell, you need 30 unit cells.
Mm-hmm.
And again, we said it scales as n squared. That's why this space is not really being calculated.
So technically we should start with more like simple ratios for calculation purposes.
Yes. So we can start. That's where eventually machine learning come in. So you have all these properties studied to death already with 1 unit. So now you will probably make a few calculations with DFT with the 30 units.
In machine learning.
And then you will train the machine learning and predict, because the amount of configurations in a 30 unit cell is huge. It's, I don't know, 30 factorial or 10 to the 30th or whatever. It just scales enormously. So if you have trained it on few examples from machine learning, it can further predict the properties without doing real DFT.
So we don't have to.
And machine learning does the calculation in milliseconds. DFT will take you 2 days to calculate.
Okay. So we just use machine learning to like narrow down the decimals, technically for the ratios.
We'll see. That's the idea. Yes. So to mix something that's, and the interesting part is that when you start mixing, that you need to make sure that it's not just an average of everything. So the machine learning should be smart enough to know that when you start mixing them,
they all have different structure.
Something interesting might happen.
Okay. So it's like we start with maybe like 50-50, and then we do like 10%, 20%, 30%, and then when it gets to like the single percentages, we use machine learning to narrow it down.
Yeah.
Okay.
Yeah, so we have done something similar for perovskite, for solar cells. So like methodology is kind of there, just making it now work for batteries. It's a matter of what the question we are really trying to answer, but that's one of the possibilities what we could do with machine learning.
So what would you like me and Philip to get started on for DFT?
Just being able to run a simple crystal. So we can start from just this
like a theoretical crystal first, and then run it.
Just ideal single unit, let's say, right? And then make it a larger unit, and maybe make it. So right now I actually have a model system, which is the one that actually is on the website as a picture. That's a real part of calculation. I wanted to make a fancy
visually. So, did you want us to do it with Niagara or Blue Gene?
Again, I need to contact the Niagara guys and see if they turn me off or they will just create another account.
And then we'll use the account, go into their servers.
Yes, so this picture is actually a real, well, it's an unfinished calculation, so it's just an input geometry for a calculation.
Oh, they have visual outputs for?
Yes, so that's what we will start with, like how to run it, where to run it. problem was that I couldn't run it because this program doesn't like transition metals, or doesn't like metallic systems, let's say this way.
So right now there's no specific transitional metal based DFT program, right? So we're actually using either the non-metal or metal, or
Yeah, it just the ones that I like the most with the easiest input. It just doesn't like metals, or like you need to play with it to make it work for metals. Technically, it should work, but just not straightforward. So what I was trying to build is like, so it's all a periodic system. So
just because they can't do like transition metal lattice formation.
Because as we've shown here, transition metals are
they're
half filled.
Yeah.
And this program works for matrices which are easy to invert, and this is only possible when filled and unfilled states are well separated.
Okay. And you said that we could define the spin difference and then put it back?
I'm not even doing a spin right now even. So what I'm trying to do, I thought, okay, I'll just build a full battery. So on the right I have a graphene, on the left I have cobalt oxide, on the middle I have electrolyte, so it's some oxychloride, this is lithium, and some organic solvent. So everything is there. So if we can run this, we can run anything.
So our input has to be like a physical representation?
Yes, so you need to define a geometry, and then you need to define all the parameters for solving it. So that's why I say when you do the DFT calculation, you kind of know the answer beforehand, because you've built this geometry, and if you build it wrong, you will get a wrong answer. And it's very easy to build it wrong. So that's why like it's garbage in, garbage out. And this is my initial guess what the system would look like. And then when you run the molecular dynamics, you kind of let the system evolve under all the quantum mechanical laws. Maybe this electrolyte will interact with the cobalt oxide and will oxidize it, and or will damage it, or will convert it to something else.
Are all the distances predefined, or like is it calculated?
Well, so this crystalline structure is known. I can just take an experimental structure, cut out a small piece, and use it. Same for graphene.
What about
this is kind of defined as well.
Okay.
So graphite there is some space between the graphite. So it has this van der Waals interactions again between them. So it's luckily so happens that is a distance between the cobalt oxide layers. So cobalt oxide is also a layered structure, and graphene layers is almost the same, so that
it's fairly linear.
I can put them in the same system. So in reality, it's a real periodic structure. Crystal cell, create cell.
Did you want us to start with this program first?
Yes, maybe. So this is just visualizing stuff. This is actually some drug discovery program, but it's just so convenient. So yeah, I will share this program and I will teach you how to use it. But basically, you can, let's say, ABC, 50-50, 10 here, apply, and we can see what it really looks like. Right, so it's system like this. So it's all periodic in all directions. So that's how DFT usually works. So it's essentially you have your two electrodes and stuff floating between them. And then you will start running DFT. Crystal structure won't change too much, but all this liquid stuff will start floating around. And ideally, I wanted to see how lithium maybe moves to the left or moves to the right. It will take forever to calculate, but it's like something very visual to show to people. But in general, it's like a first step to make sure that we know how to calculate, how to run
this type of system. And that's where I get stuck because it doesn't like the cobalt oxide.
So this is just visual representation. This isn't the DFT
Hmm?
This isn't the DFT program. This is just a visualization.
This is just a visualizer.
Okay. Yeah. Okay.
Yeah. And the DFT program, well, we'll talk about this tomorrow probably. But so this file is just XYZ. It's just the coordinates of atoms. So if you look at it, it's just atom and its 3 coordinates. So I have 300 atoms here. So it's fairly small system. So it should actually run super fast on this blue gene with 1000 cores. 300 atoms is like nothing if it converges. So the problem is that it doesn't want to converge. And the input file is also fairly simple. That's why I like this program. And so it says restart if you do restart. So run type cell optimization, like optimizers. These are almost default. So what we are doing, geometry optimization or molecular dynamics. So yeah, so this molecular dynamics, we want many steps, 3 femtoseconds per step. We define temperature. So basically what molecular dynamics is you do a DFT as we did, and DFT tells you the n. And now you give some velocity to each atom, so to represent the temperature. So now you start to shake them, and if you shake it away from its stable position, this density will define what the force that pushes this atom back. Okay. So your system in a standard DFT, so this is energy, it will sit in the lowest energy configuration. That's what it will do. But in molecular dynamics, you shift this system out of equilibrium, and this non-equilibrium will create a force which will push the system back.
It's like the recovering energy.
Yeah. So basically your thermal energy, so everything wants to get to this minimum of energy, but your thermal energy will give you this extra. You can go away this much because you have your thermal energy.
So we're adding in parameters that we can make it simulate actual conditions.
Yes, and it's almost a classical simulation. So you have a set of atoms with the classical forces acting on them, except that the forces themselves are calculated based on this density. So the calculation of forces is quantum mechanical, but the movement of atoms is completely classical. So it's basically you are shaking your atoms, and if it's a solvent and nothing is attached, so a crystal doesn't have too much to shake. But if it's a liquid, this molecule can go anywhere.
And then we can know like the breaking point.
Well, yeah, so the step that we simulate is femtoseconds. For anything to happen in a real system, it
takes a while.
Microseconds, milliseconds. So it's a million of time longer. So instead of one DFT calculation, you need to make million DFT calculations on every step. Every time step, you do a new, fresh DFT calculation.
This is just calculating like the cycle of...
Yes.
Okay.
Yeah.
Okay.
Well, if there is something that is too reactive and wants to transfer electrons somewhere, you will see that the molecule wants to react. It has to react with what? So you will see something happening. If not, then you will just see a floating liquid of stuff which doesn't change over time. So again, this calculation is not super useful, but just making sure that we can run it.
Okay. So right now, our plan is to get the lithium battery out, the basic, and then we make baseline for all the DFT calculations. And then we do DFT calculations for doping, and then we check experimental data for the doping to see if it correlates with the theoretical.
Yes.
And then we do back and forth.
And especially, usually it works vice versa. Usually you do experimental, you have mixed, I don't know, nickel manganese, and you decided to add cobalt there or titanium. And suddenly your battery starts working better. And then the question, why?
And then you go back and
then you go back to DFT, you build the system, you check the right crystal structure, and you calculate maybe its electronic properties, or maybe your Fermi level have shifted somewhere here or here, or maybe you have removed these intermediate states completely, and that's why it's like behaving better. So it gives you better voltage, because like this would be your voltage, let's say.